All right, and let's try one more time. All right, so now this is behaving as an inflatable, but it probably doesn't look like what we might expect an inflatable to look like. The reason being, it might look more like a grid shell, but the reason being is that the way we've chosen to constrain this is based on just points, right? If we're wanting to inflate this as a volume, we're not going to use just a few anchor points, but we're going to use more likely the entire edge, right? So we'll bind an edge or constrain an edge across the entire shape and then inflate it. All right, so in order to do that, let's use a different one of the utilities under Kangaroo utility, and let's grab the naked vertices. These are all the vertices that have only they're at the far edge. There's no face on the other side of the edge that corresponds to them, right? So we're going to take our mesh from here. These are going to be our naked vertex points, and I'm going to put that into my all anchor points. Reset my simulation, and then let it simulate again. And now we're going to get something that looks more like an inflatable, and we can allow this to stretch more. We can increase the pressure, resist it again, increase the pressure. All right, and now if we wanted to manipulate the initial shape, we're going to have to go back to changing the control points of our mesh. All right, now this is relatively interesting. Notice that if you go too far beyond 1, that's the situation I was mentioning before, where the mesh starts to kind of get a kink in it, right? So this wants to be about 1. So if you want to make your inflatable volume taller, you're going to have to increase the pressure. But again, if you go too far, it can break, right? So you have to kind of calibrate that as you go. Okay. So this volume is pretty interesting, but let's go ahead and work with now the kind of visualization with analysis built in. So I'll turn off these other objects beforehand, and let's go to, by pausing the timer, let's go to the mesh and let's look at a different way to color each vertex, right? We looked at distance, we looked at height, we looked at Y value, we looked at spring length. Let's look at how far that point has traveled from its initial state, right? So what we're going to do is we're going to bring the initial vertices all the way over into just a point container. This is a way for us to translate geometry from one part of the file to another and have a place to label it. So this is our original vertices. Right? So we'll test then the distance under vector point distance, the distance from the geometry out to the original vertices, and then this distance, we'll do the same thing that we did before with our gradients, right? We'll find the bounds, we'll decompose the bounds, we'll make a gradient object. I'll make this white. Drag that grip over. And right now, to get the grips to work, you have to double-click them in the grasshopper canvas. Maybe purple, or is this called fuchsia? There we go. All right, so start, end, and distance value, and use that to color my vertices. All right, so this tells me how far the surface has traveled away from the original position, which is useful if we're trying to understand where the kind of most flexibility is within the surface as it as pressure is applied to it. All right, so I'll reset this and we'll watch it run one more time. All right. And then one more thing I wanted to show is that you can hybridize a kind of automatic edge condition and something internal to the into the original mesh. So let's say I wanted to create a column within my inflatable around here. Well, I can take this mesh and bake it real quick so that I have the vertices to snap to, add a couple of points in here, and then because I've got this merge working, I've got the naked points and I can supply my own input anchors. Right? So now I have internal controls that are more manual that I can start to work with. Right? I want a column to be located here, right, so that I break up my space, or maybe it's related to structural issues. I can take these vertices and start to say, okay, well, there's actually going to be a raised platform that this is going to start from, so I can start to work with the inflatable and stretch it, and kind of sculpt it in a way that is more based on kind of my design inputs and less based on the nature of the original geometry, which was just these simple mesh faces. Right? And you can do that as many times as you want, right? As many positions within the inner part of the mesh. All right, let's take a couple of questions now. The points that I just used for anchors, my process for specifying where they should be, because they have to be co-located to one of the vertices of the original mesh before it's simulated. So what I did was, if I go back to delete all those, this is just grasshopper geometry right now, the subdivided mesh. So I'm going to bake it by right-clicking. This is here, the triangulated mesh. So now I have that mesh as a piece of geometry in Rhino. I can specify points wherever I want. I'll try a two-column system this time. And then bring those points back into Grasshopper, right? Let my simulation go again. Now I have those points that I can start to manipulate. Now, if I start to stretch them out of the XY or move them at all, I need to make them be back in their original position before I run my simulation again. Otherwise, they'll be lost as anchors because they won't be touching another point within the simulation. Right? That's a good question. There was a question about exactly how the pressure force is working. It is working perpendicular to the face of the mesh. So if you imagined that here at this mesh, I'll just draw this really quickly. At the center of the mesh, if there is a vector that is pushing on it, right, that's how the pressure is working. Of course, it changes as the simulation runs, right, from being essentially up everywhere at the initial state of the simulation to swinging around and moving perpendicular to the face at the current state, right? That's how any pressure system would work. Like when you blow up a balloon, right? The balloon is changing, but the pressure is still being applied perpendicular to the face. So if I wanted to just very quickly show those directions, I could grab the face normals from my mesh and preview the vector that goes along with those. All right, so you can see them all pointing perpendicular. If I reset my simulation, right, the pressure is always being applied along that vector. All right, so I'm going to pause the timer. I'm going to maximize this because there were some questions about where some things were being connected from. So as I do this, or as you take a look at all the connections, I'm going to go ahead and label everything again like I did last time so that you have this as a reference. All right, so and I won't zoom in or anything. Let's see, this is our quad mesh. This is springs from mesh. Mesh decompose. And while I'm doing this, if you have any other questions, go ahead and drop them into the question window. This is pressure. For subjects, this is distance here. Bounds. Domain decompose. Parts. Mesh. Gradient. These are our base normals and vector display. All right. All right, so it doesn't seem like there's any more questions, but there was one comment that if you look under utility where we've been working in Kangaroo, you'll see that there is a mesh pressure utility. This would be a way to circumvent the taking apart the mesh and recomposing it. But I thought that that was a useful kind of set of steps to go through in this exercise with working with the meshes. So if you do this, this is just like the springs for mesh. You essentially put in a mesh and supply a pressure level, and all of this goes away. All right, so I'll save this and then save it as a second version with the mesh pressure object. This goes here, this goes here. We don't need this any longer, or these, but we do need to keep the mesh decompose. Okay, because the decompose connects back over to here. All right, so that's the second version for you. Okay, great. Let's save this. It doesn't seem like there's any other questions, so let's go ahead and bounce back to the presentation.